Okay, just now we learned about what these crystal engineers do and what are the steps involved in getting to prepare materials that has got the desired physical and chemical properties. Now we want to discuss some of the historical uh, uh, things that has that develops this particular area of crystal engineering. Um, not moving. Okay. Okay. If you think of the development of crystal engineering, it has to start with determination of crystal structures anyway, from the point of view of crystal engineering. Okay. From that point of view, it has to go back to William Henry and William Lawrence Bragg work on single crystal X-ray. Yeah, you all know about the story, right? I mean, this is father, this is son. Actually, he was, this guy is British, but he went to Australia, Adelaide, and then he was born there. And he was a professor of physics. And he came to England to work on X-ray tubes. Actually, he is very good at, experimental skills. And then, whereas this guy is the one who derived this Bragg's law. And both of them work together, in fact, and for the, they determine the crystal structures of very small molecules like from sodium chloride. There are so many things they determine. They are the father of, X-ray crystallography. But he won Nobel Prize actually, 2019-12, I think they determined the crystal structure. He started working, doing the research, and I think 1914, he got the Nobel Prize within 2 years. It was just 21 years, one of the youngest in those days, but now that they have been replaced by a few people. But at the time, you see, okay, so this is the youngest one because, the X-ray was, the structure determination was developed by these guys. And visualization and crystal as a periodic array, and unless you see how the molecules are arranged in the crystal structure. Is first organic compound. I'm not talking about the inorganic compound, organic compound, hexachlorobenzene, urotropin are the first one to be determined. And at that time, they can only determine from the crystal structures. They started asking questions. Given the molecule, you just started writing some molecule, what should be its crystal structure? If you know how to predict that, that'll be easier. We don't have to, get the single crystals and do all these things. But nowadays, people started working on this. This is becoming a big area of research. By writing down the formula and structure, you can predict the crystal structure. And later you can go and make it, and they show. I'm going to talk about it today or tomorrow. Let's see. About the computational way of predicting the crystal structures. So it is possible. But that's a first question we ask as a crystal engineer. If you know what is the crystal structure a priori just before we started making it, then we can change the molecular structure accordingly, so we can get the properties or the packing we want. Okay, so if you see the development, and it all started from 2+2 cycloaddition reaction, because that's the one. The work of Gerard Schmid is responsible for the creation of you see the crystal engineering, as you see here. This 2+2 cycloaddition reaction was known for centuries. Lieberman was the one who has done this. But later, 1943, Jack's paper, Bernstein and Quimby was the one who wrote first thing about the 2+2 cycloaddition reaction in the solid state. In the solid state, if you see, there's not much deep into the reason for this behavior that was discussed by Bernstein. And later in 1955, Pipinski was the one, he used the term crystal engineering. And again, it was only in the abstract of American Chemical Society. There's nothing else. It was just an abstract. He used the term crystal engineering. But later, the Schmid, he started working in 1960s. He started working on this 2+2 cyclic reaction. And again, there is a history. I mean, Bernstein was the one who was in US. He went to Israel, to the same university. I forgot the name of the university, where Schmid was working. Schmid got his master's from who's that? Robert Robertson, master's, and Dorothy Hopkins, PhD. After that, he went back. He started his own career, but he was not working on any of this. Crystallography. Both these guys won Nobel Prize. And then when Schmid went, and Bernstein, went there as a dean, and he started asking Schmid to work on 2+2 cyclotron reaction because he's got very good background with crystallography. Then he started working on that. So in 60s, he published a lot of good work in 71 based on the photochemistry of some of the compounds containing olefin bonds. I'm going to explain here very briefly. And later, he was the first one who correlate the structure and reactivity. Is structure and property. Property may be physical or chemical. So first he predict, how chemical reactivity will depend on the packing. So he made, he crystallized cinnamic acid in 3 different solvents. He got 3 different polymorphic modification in alpha form, the double bonds. This is the structure of cinnamic acid. You see the alpha form and the beta form and gamma form. You see the double bonds are nicely alike, and the distance between them is less than 4.2 angstrom. And in one form, it's in the phenyl, and the phenyl rings are in opposite. It trans head to tail manner. The second one is in head to head manner, and again the double bond aligned in parallel, and the distance is about 4 angstrom. The third one, the distance is more than 4 angstrom. But the packing is very similar to the previous one. So if you take this particular compound and put it in under UV light, it undergoes photodimerization and it forms this particular compound. And it's the cyclobutane derivative in 100% yield. Within few hours. So you take a solid or a single crystal and then put it under UV light, and you get the product in no time. Whereas in the second form, the same thing, the reaction occurs in the solid state under UV light or even sunlight. Many people do the reaction sunlight. So it undergoes cyclization, forming this. You see that these 2 cyclobutane derivatives are completely different. So you don't have to go through different steps to make this kind of cyclobutane derivatives. It's a single step reaction. Whereas the third one, you see the distance between them is too far away. Because of that, there's no reaction. It's photostable. And he concluded that, the alignment is important, whether it's parallel or not parallel. If it is parallel and if the distance is less than around 4 angstrom, then the reaction occurs. It's called Schmid's rule. Later he developed, and still we are using. As long as it follows the Schmid's rule, we can predict them to be photoreactive.
Sir, I have one question. There are several papers that if the distance is more than 4.2, still they.
We'll discuss about. At the end, I'll take your question. I can talk about it a lot. So what happens if you take a single crystal and then do a reaction? At the end of it, you get another single crystal. This is called single crystal to single crystal reaction. The other thing is what is the see, he proposed what he called Schmid's rule. Why it is so important? But nowadays you can explain based on Woodward-Hoffman rule why UB is important, because PZ orbitals should align, and then there should be orbital matching, and that will happen only under the higher excited state under UV light. So the PZ orbitals should overlap. unless they are not, unless, if they have to be parallel in order for the PC orbitals to overlap. And also orbital matching. Those things will explain, the distance is, if it is less than about 4 angstroms, then the overlapping is significant. So the reaction will occur. If it is very far away, there's no overlapping, no reaction. So now we can, So, but anyway, so he is considered to be the father of organic solid state chemistry as well as crystal engineering, because he tried to explain the correlation between photoreactivity and the solid state package. So later, a lot of people are working on this, like, when they're all their students. Okay. So in fact, when this 1971 paper is a milestone paper, this was written by then he died actually after his death. His students wrote his paper. It's about more than 50 years since he discovered this, and many people are involved for this development of crystal engineering using the photochemistry. Now, okay, you have to do okay. Now I need to connect, a few things. Now, supra molecular chemistry. I'm sure, here I'm going to convince you, crystal as a supramolecular entity. Okay? Are you familiar with supramolecular chemistry? You might have taken many of these courses. And it's nothing but molecular assemblies. And between, you'll have two different, compounds and interact with each other. There are a lot of principles behind it, lock and key, and similar such things. But I'm going to talk about it maybe later a bit more. But this supramolecular chemistry signifies, what is beyond the molecule, because you always talk about molecule. You talk about the interactions between different molecules, and it's an interaction beyond the molecule. It's concerned with strategies for controlled organization of multiple components into complex matter, because normally it will be a cluster kind of thing. It's a discrete kind of entity, and different molecules are interacting with each other, through supramolecular interaction. Supramolecular is nothing but these hydrogen bonds, the weak interactions, non-covalent interaction. I'm going to repeat this quite often. They're all synonymous. Weak interaction, supramolecular interaction, non-covalent interaction. They're all coming under, that is not covalent bonds or coordinate bonds, hydrogen bonds, and the bonds having less energy. So in the context of crystal engineering, because we always talk about supramolecular, entities mostly in solution. What Lane and others talk about it, mostly in solution. And in the context, the crystals are considered to be supramolecular system because all the molecules, have got supramolecular interactions. So you can call that an ordered supramolecular interaction. So the crystallization is an impressive display of periodic molecular assembly. So when you try to make this kind of any crystals, molecular crystal structures, so you are synthesizing a compound. When in the molecule, when you synthesize the molecule, you create, covalent bond between the atoms. But when you create a crystal, you create non-covalent interactions. So you can also call it, when you crystallize something, you say you synthesize a crystal. Okay. So I'll talk about the work of, this more a bit later. No, one is not able to do that. You would see that this kind of supramolecular interactions will usually these are all weak interaction. Although they are weak interactions, some of the stronger non-covalent interactions, such as hydrogen bonding, will lead to connectivity. When you can describe a molecule, usually when we think about molecule, it's especially the organic crystals and molecular crystals, it's a collection of molecules. But whereas if they have some directional interactions like hydrogen bonds, and you can talk about network structures, just like inorganic network structures. How it is possible? I'm just showing you here. This is an adamantane tetracarboxylic acid. Usually they form a dimer, something like this, between carboxylic acids. So if you represent this adamantane like this methane compound, so you can determine the crystal structure of adamantane tetracarboxylic acid like this, where this acid this acid dimer, hydrogen bonded dimer, is shown in this like this bond, and this one is adamantane, like shown in here. So when you convert the crystal structure of this particular compound into this entity, this is nothing but the structure of diamond. Okay, you see the correlation between them. So immediately inorganic, compound having this type of diamondoid topology or adamantanoid topology, cubic zinc or zinc blend structures, they also have very similar to this, the connectivity. So you see the connection between the inorganic and organic compound as when you have the connectivity that you can describe in terms of inorganic network structures. That becomes easier for us to understand the interactions in the solid state. So, okay, I'm going to talk about the molecularity and the dimensionality. This one. Okay. What is a molecule? If you have naphthalene or even methane or sucrose or anything, if you draw XYZ in that molecule, you started walking on the covalent bonds, you see the end along X, because after that, there's no more covalent bond. You'll fall into big interactions. Okay, Y direction, same thing. So it's a molecule, you know that, because they're all discrete. Is that same thing? So they're all discrete along X, discrete along Y. So when you have naphthalene, the molecularity is 3D. In all three directions, it's molecule because it's finite. So in terms of dimensionality, dimension is endless. It's infinite. Okay, so this is because this in all the three directions, there's a it's finite. It's not infinite. So it's a 0D. If you take palladium chloride, the structure is shown here. This is naphthalene. This is palladium. You walk along this direction, it's infinite. Along this direction, it's not molecular. It's not a molecule. If it is a molecule, there's a finite, there should be an end to it. So along this direction, it's not molecular entity. But along this direction, it stops here, molecule, because it stops. There's no more covalent bonds. Along another third direction also. So it's a 1D in terms of, go back. This is 1D in terms of dimensionality. We know 1D polymer. This is 1D polymer. But in terms of molecularity, it's a 2D. You understand? Okay. Graphite. Graphite. Okay, these are all pi interactions. We know that it's a 2D extended covalent bonds. But in terms of molecularity, it's a molecule only along is a direction because it's finite. So if you go back here, graphite dimensionality wise is 2D, molecularity wise is 1D. Diamond, again, it's a three-dimensional structure linked by covalent bonds in all the three directions. So it's a 3D. But in terms of molecule, you don't see the molecular nature in all the three directions because it's extended. So it's a 0D in terms of molecularity. So this is the correlation, Pitagoretsky trying to mention what is the correlation between molecularity and dimensionality. Usually students will get confused because I always show this. This is half. What do you say? This particular cup is half filled. With water. So same thing with the air. So you can say dimensionality and molecularity. They complement each other. So that's what we do. It's another way of describing molecularity and dimensionality. Okay, you don't get confused. Okay, the timeline. Okay, I'm going to take another 2 or 3 slides to show some of the things that is given in the book. You can always, timeline, you can put in anybody's work here. Anyway, we are very selective in putting Bragg's work, crystal structure. He was the first one to determine organic compound, and then Bernal is the one. He said groups of crystal structures, correlate and how they are related, and how you can talk in terms of similar type of interactions. And Powell is the one again he described this the hydroquinone as a structure, network structure. Lipinski again he defined the crystal structure. Schmitz I talked about it. And in 1964 he has published papers, but only 71 he talked about crystal engineering, and he correlates engineering of crystals, especially photoreactive crystals. Yeah. And again, this is Professor Desiraj's book. So it was written accordingly. So Desiraj's book on crystal engineering, this is one of the timeline milestone. And this Robson's work, actually, this is described how to make porous CPs. So if you, and many people think that if you need to give a Nobel Prize for MOFs, his name should be first in the list, along with maybe Yagi and Kitagawa. And Yetter, Maggie Yetter, who died due to cancer in 1994 or 94, identify hydrogen bond as an important design element. Okay, we are going to talk about the graph notation to describe hydrogen bonded patterns. And Dönitz is another guy who talked about correlation, talked about crystal engineering. He says crystal as a supramolecule par excellence. Okay, supramolecule. And verse in before Desiraju here, Jim West introduced the term tectons. I'm going to talk about tectons. This is one of the milestones. And then synthon was introduced by Desiraju in 1995, and Yagi is the one who described the gas option. Also, he made a lot of cross structures. The first book on engineering. Of course, the first meeting was held on crystal engineering was held in Erice. That was the first meeting because it's a recent one. Because initially it was just the crystal structure determination and then molecular structure, interest in molecular structures. And later they started looking at the interaction between the molecules and then what it can do to improve the properties of solids. And again, this is another earlier meeting that was held in Nova Scotia. Zavararko was the one. Probably you are familiar with many of this. They might have, I'm not sure whether they have visited. It's just a new campus, right? But maybe in other IITs and IITs they might have visited. And again, this is the first Gordon conference. You see that it's me attending. It was in 2010. All these pictures. I will go to the organization of lectures now. As I already mentioned to you, I'm going to talk about intermolecular interactions next. That's a full box of crystal engineers, different types of interactions. And how do you use these interactions to design, is a crystal design, how to design all these things organic. And then I'm going to jump to coordination polymers. And this is all, or you can call it as metal organic framework structures. And then how crystallization is very important, because that's the only thing, unlike organic synthesis, it takes different steps. Whereas to make this crystal synthesis or the supramolecular entity, in the solid state, there's only one way we can do. That's crystallization. Is just put everything into solution and whatever you get out of it. But we can talk about it. That's very important in getting this crystals and polymorphism. How we can get different crystal forms and what it can do. What are the importance of these things? And then multi-component crystals. And I think that's about it. Okay. So you see applications anyway, and you can add more. In fact, nowadays you can put it in many other engineering areas. Materials can go into You can talk about different types of materials. You can building materials from electronic materials and all, and drugs, of course, sensing, catalysis, and so on. The applications we are going to see. Move on to. Excellent. Do you have any questions so far? Yeah, we can discuss later. Okay. So I'll come back to your question. Okay.
Yes.
Actually, that becomes a different subject. Okay.
Oh.
So maybe when I give a scientific talk, I can talk about it. Okay. Or we can discuss later. Okay.
No, sir. Just a minute. It is not visible in slide. Means for this online paper. Yeah. Nice.
Okay. So now we are going to talk about intermolecular interaction. So this is from the crystal engineering toolbox. We are going to talk about different types of non-covalent interactions, weak interactions. So, right from van der Waals and to strong hydrogen bonds, okay, and then a lot of other weak interactions, halogen bonds, other metal pi interactions. There are so many that are present, and how to study such interactions using different methods, and some graph sets and some of the things I'm going to talk about it. Thanks. I don't know why.
If I click somewhere else, then again I have to click.
Okay. All right. And the learning objective. So here we are going to talk about intermolecular. This is nothing but intermolecular interaction. If it is intramolecular interaction, it's within the molecule, which is not our concern, because that's not going to get the packing. So intermolecular interactions are very important, and why they are important, and some of the general principles. All these weak interactions, we are going to cover under this subject. Organic is, I think I mentioned to you about, is a collection of molecules in the solid that becomes molecular crystal. So there are, what is there, is weak interactions, and because they are all very discrete in nature, it has got advantages as well as disadvantages. What are the advantages? I mean, see, as I mentioned to you, okay, this is nothing but weak interaction, supramolecular interaction, non-covalent interaction. We're all saying the same thing. Okay, they're all synonymous. Okay, so as far as kinetics is concerned, is kinetically favored. You can control them kinetically because crystallization is a kinetic phenomenon. You just resolve them very easily, as compared to extended solids like MOF or inorganic extended solids like zinc sulfide. Okay, so it's very difficult to dissolve them. So once they form, it's very difficult to break the bonds. So thermodynamically, they are very stable. The intermolecular, I mean, here you can't distinguish between intermolecular interaction and intramolecular interactions. Everything is the same. Whereas here you have got distinct, intermolecular interaction, intramolecular. Intramolecular is nothing but covalent bonds. Inter is also supramolecular interaction. So advantage is easier to crystallize, easier to control crystallization. Disadvantage is, they are all very weak. Because of that, stability becomes an issue. Okay, so this crystal engineering is divided into three parts. Understanding of intermolecular interaction, that's what we are going to see. And then developing strategies planned by which these interactions can lead to certain desired packing. It's a design principles that I'm going to talk in the next part of the lecture. And fine-tuning, how we can change it. When we talk about applications, you can very easily show that how you can modify some of these properties. So again, when you talk about intermolecular interactions, I have to refer to this potential energy diagram. We are all familiar with. Whenever we talk about the formation of hydrogen, this is what we do. It's exactly the same for intermolecular interaction. In the case of molecules, for example, hydrogen, we bring two hydrogen, H, okay, hydrogen atoms. But in the case of molecules, you bring two different molecules closer. That's what we do. It's exactly the same. So when you bring, naphthalene, whatever, aspirin, close to each other, the interactions, usually they'll have hydrogen bonds, they'll have pipe interaction, they have different types of interactions, what happened. So because of that, the energy will be going down. The energy will be released here, so it goes down here. So it reaches certain stage. After that, if you push it together, there will be resistance. So it goes up. The energy goes up after a certain distance. This is equilibrium distance. When you bring two different molecules, so they interact through supramolecular interactions, and the energy is minimized because the energy is released here. And then repulsion, it becomes attraction equal to attraction, and this is how you can explain. But you can also talk in terms of forces. Forces in terms, because whenever you have weak interaction, that will be attractive. They attract each other, just like covalent bonds. So because it's attractive until then, okay, it goes through a long distance range here. Once it reaches, you cannot bring it closer anymore, and then it becomes repulsive. Even in the case of supramolecular interaction. So this is how you try to explain this potential, the same potential energy diagram that you use it for, covalent bond formation. Here, this is intermolecular interactions. In all these things, in all the intermolecular interaction, the energy is of this range, 0.6. This number varies from textbook to textbook. I just mentioned 0.6 because 0.6 is of the order of kT, Boltzmann constant times room temperature. That's about 0.6 kilocalories. So it's about 30. Some people say 25, 35, it doesn't matter. This is a ballpark figure of intermolecular interaction that can occur in this range. And also we know that 1 kilocal is 4.84 kilojoules. You can convert it, and I'm going to talk. We usually discuss in terms of kilocalories per minute. Again, I should have discussed it somewhere else, but we put in the Jean-Marie definition. It's beyond the supramolecular chemistry, and then these molecules are held in supramolecule by non-covalent interaction. So he says that Jean-Marie Lane, says that this supramolecule, supramolecular entity, but now in terms of crystal, we call it supermolecule. And then, as I mentioned to you, it's a crystal syndrome. Crystal, a supramolecule is nothing but crystal from crystal engineering point of view. So you can talk in terms of interaction, attractive and repulsive, or stabilizing. In this case, it's stabilizing, it's destabilizing, attractive, repulsive, in terms of energy or in terms of forces you can describe. And general properties of this interaction. Let me talk about the covalent bonds. The covalent bond is in the range 75 to 125 kilocalories per mole. You agree? Also the carbon-carbon. But the strongest one is nitrogen triple bond. Is the highest, 226 kilocalories per mole. The weakest one is carbon iodine bond, is 30 kilocalories per mole. I think non-covalent interaction, see here, previously I had given 0.6 to 30, but now I had given, see, I'm just contradicting what I had given. So this is the ballpark figure, but you look at the hydrogen bond energy here, the strong FHF. 50 kilocals. Do you believe it? It's very, very strong, stronger than covalent bond here. So this is an exception anyway. As I mentioned to you, KT is about 0.6. That's why, that's why some people argue that don't give 0.6 as the lowest one, because 0.6 you can't do anything with this kind of energy. So bond energy should be more than that. That's why they have given 1. Okay, that makes sense. Makes sense. So whenever you have this kind of interactions, you can classify them into strong and weak in terms of interaction. Yeah, weak and strong. So if it is weak, it's directionality. I'm going to talk about the directionality. And isotropic. If it is weak, it's isotropic. If it is strong, it is anisotropic. Think about van der Waals. Think, if it is weak, think about hydrogen bonds. If it is strong, it has got directionality. That is anisotropic. It forms hydrogen bonds only in certain direction, whereas van der Waals is in all the directions. So, this is a comparison. Weak means van der Waals, strong means hydrogen bonds. So isotropic, anisotropic. Distant dependence is dispersive. Van der Waals is dispersive, whereas hydrogen bond is electrostatic. So you see the difference. Okay, so it has got all advantages and disadvantages from crystal engineering point of view. But you can't control. It has to be present. Both should be present. But if you have very strong interactions present, then you have anisotropic directionality. So it forms in a certain direction. That will lead to the prediction of crystal structures. You can predict, you can try to form, align the, or pack the molecules using strong hydrogen bonds in a particular way. Okay, that's an advantage. Okay, so weak interaction, you have no control because it's all isotropic. Like take, for example, argon, it's spherical. So you try to pack them. You can pack in any way. It's a ball, like take a tennis ball and try to pack it. It's very weak. But why it is important? Why are we talking about it? Because this kind of van der Waals interactions are present in plenty. A lot of van der Waals interactions are present, although they are very weak. When you have large number and then multiply by a small number, it becomes large. 1,000, of interactions, and even if it is, 1 kilocalories, and then versus, 1 hydrogen bond with 30 kilocalories, you can compare. So in terms of the stability of a molecule, so it depends how much is this kind of van der Waals is present is very important, or weak interactions are present is important. That will also sometimes dictate the packing. When you have weak interactions, we have no control on the packing. That's the only thing we need to remember. So we always compare the Gulliver effect. You see the Gulliver, all these small guys, they are large in number. They are able to catch this guy. So your Gulliver travels, you might have seen the movies and everything. So the Gulliver effect is very obvious. We always compare with van der Waals interactions for this Gulliver effect. On the other, we always say that this is another thing. Gecko's feet, they try to climb. How it is possible because of van der Waals that is present in large quantity in their thing. So I think there is a science paper or nature paper that was in the 90s, I remember, explaining this, geckos, how geckos are using van der Waals interactions to climb up on the walls. So that is very important. They use nothing but van der Waals, so you can very easily break the bonds and form the bond. Okay. On the other hand, directionality. If it is directionality, if you think about hydrogen bonds, you see the ketone has got two lone pairs. So if it has to form hydrogen bonds, it will be in these directions. And same thing here with the ether. So it's directional. So directional is important, is for designing, but not van der Waals. But you can't get away from van der Waals forces that is always present in the crystal structures. But for designing, it's not that attractive. Okay, again, let's talk about van der Waals interactions. Again, we can use the same diagram, potential energy diagram, to explain the Reynolds-Jones expression for this potential energy diagram. And it has got, A and B. This is attractive, repulsive, and this is electrostatic. You're all familiar, probably. And the attractive one, the distance dependent is r to the power of -6. The repulsive is -12 on this side. This is -6 on this side. The electrostatic is nothing but hydrogen bonds, Q1, Q2 on the charge on the two atoms, and then the distance dependent is -1. So this will tell you how strong and how weak are these two different types of interactions. In the case of van der Waals interactions, okay, on this side, it falls very quickly because r to the power of -6, it falls very quickly. And then this side is, this is again is smaller than this side. Whereas electrostatic, because of the inverse dependence, its attractive force is in the long range because slowly it falls off. Okay, so because these things you need to remember. So if you want to design the topology and connectivity, interactions should ideally be both strong and directional. Okay, obvious. So it should also be operative at long distance. So the packing efficiency, but to optimize the packing efficiency, interaction should be non-directional and short range. Because if it is directional, you keep the another molecule at a particular distance. Whereas if it is spherical, if the interaction is an isotropic and there's not much energy, you can pack them very closely. Okay, so that's the thing. So the packing efficiency and density of the compound containing van der Waals will always be very high. Okay, so that's the thing. I'm going to show you, in fact. Okay, so this is the one I'm going to show you. This is close packing. Whenever you talk about van der Waals, and you can think of your molecule with spherical shape. If you have a spherical shape, you can pack them, close pack them in two different ways. This is first year, or even I don't know, maybe in high school. Packing, close packing, HCP and CCP. Different types of packing you can do. If you take in HCP or CCP, each molecule is surrounded by 12 nearest neighbors. 12. So coordination number. We don't say coordination number. The nearest neighbor, coordination number. We always say that it's 12. Yeah. But according to Pythagoras, he's a Russian guy who wrote a lot of books, and it's very difficult to understand. Even after translation, to understand his writing. But he has done a lot of work on that. Maybe you may have some books here. Translated, but he is the first one to talk about the crystal engineering principles in terms of close packing, especially van der Waals interactions. And according to him, the maximum number of neighbors is 12. But in reality, if you take a look at it, it is not so. In close packing, you cannot expect 12 for a few reasons. Even if the molecule, I'm not talking about the atom, it's a molecule. They're not spherical in nature. Even if you remove all, this iso, tetra, methyl, tetramethyl, methane kind of thing is spherical. There, or if you take it, probably for that packing, you can have either HCP or CCP with a number of close neighbors equal to 12. For other natural molecules are not spherical, they are flat or different shapes and sizes. If that be the case, the close packing is not possible for this. And when you introduce some kind of directionality of bonding, then it will be reduced closure. Anyway, so for example, here, if you have a hydrocarbon, CmHn, carbon-rich molecule, where M over N is more than 2, for example, coronium, they stack, they nicely stack. Whereas naphthalene, where it is hydrogen rich, they pack something like this. Okay, the packing is herringbone kind of packing. So when you calculate the number of molecules around each one, it is not 12, maybe 8 or something. So Kitayar-Goretsky model for close packing fails, because of this. Although he says, okay, it's only 12. Yeah, I mean, this is how you have the packing of molecules in the crystal structure. You don't leave any space. Okay, we always refer to Escher's book on Horseman. There are so many very nice pictures. There are few books available on Escher's drawings. So usually you see in the internet and other places and see they try to pack it. This white horses are in one direction, red horses are in the other direction, nicely packed. The packing efficiency is 1, which is not possible in reality. That's why the packing efficiency you can very easily calculate here. The efficiency of packing here. This is the volume, the what is it? Molar volume. It's a volume of each molecule times number of molecules in the unit cell divided by volume of the unit cell. So in the unit cell, you have certain number of molecules, but they are not arranged in a close packed manner, and also there will always be some void. So in order to find the packing efficiency, this is the formula they use. Always it's about 0.7. Even for CCP and HCP, you have only about 0.7 or something. It's not 100. If it's equal to 1. So the packing is not always very high. But in organic compound, it would be very, very less. Even 0.5 or something. So Kitayar-Goretsky model fails because he assumes his assumptions, are some of the assumptions are given here. So that fails because of this size and shape and other interactions that are present in the molecules. They always break down. So, but anyway, that's a good model to think about, and especially for determining the crystal structure. They always methane, ethane, isopropane. They try to use because there's no other interaction except van der Waals forces. They use it. So there probably you may have positive results, based on these principles. But otherwise, it's not possible. Okay, this will tell you. See, when you have directionality, when you have strong hydrogen bonds, the coordination number. If you look at it, ice crystal and diamondoid type of network structures, you see coordination number is 4. If you have something like this, it's predictable, but on the other hand, the efficiency, there's got directional, strong hydrogen bonds, directionality is maintained, but the coordination number is very 4. 4. It's not packing, what is it? The close packing that is not always possible. When you talk about the packing, especially of a molecule without heteroatoms, you consider its shape and size, the packing. That's why I talked about hydrocarbons. Hydrocarbons, you don't have any direction, very strong hydrogen bonds or something. So you look at the shape and size and try to pack them. So when you will have, when you try to pack that way, if the size of the groups are quite similar, they occupy the same space. For example, you take this compound, you put X here, X can be methyl or it can be chloro. When you try to pack them, exactly they pack, just like, if you take a chloro compound, and determine the crystal structure. If you have methyl group, and determine the crystal structure, exactly the act in a similar way. Because the size is the same and it doesn't have any other strong interactions. What the chloro, okay, you can say that electronically, but not much. But methyl group, the size is more or less the same. So if they have same crystal structures, we call it, they're all isomorphous crystals. So whenever you have a crystal structure with chloro derivative, you can expect the same for methyl derivative. If you crystallize together, you will get a disorder. In one molecule, you have methyl, the other one you have chloro. It's completely a disorder. Because of that, because it's isomorphous crystals by exchange. Chloro, we commonly call this as chloro-methyl exchange. In many cases, it helps because in research, you try to crystallize something with methyl group, you may not be able to crystallize it, or you may not be able to make them. So replace it by chloro compound. It's exactly the same. People will, accept that it has got the same crystal structure. Even if you don't have single crystal, you can just powder. You can just record it should be the same. You can very easily determine the crystal structure. So it's called isomorphous replacement. Crystals by exchange. There are so many like that. See, if you have a phenyl substitution in your compound, if you have thiophene substitution, both will crystallize. They occupy the same space, and they will have isomorphous crystals by exchange. So it will have the same crystal structures. Nothing. There's no difference. I'm going to show you in another, next slide. So there are so many. There are so many pairs like this. Phenyl and thiophene. There are a few more available. Probably I'll give you as an assignment, for you to find out. So chloro versus bromo, also bromo versus, but not bromo versus methyl. So chloro versus bromo, whether you make chloro compound or bromo compound, they are going to have the same crystal structure because of the size and shape. They will occupy the same space, same way they are going back. Okay. Yeah, this is an example. This is a long time ago. One of my colleagues asked me to determine the crystal structure. He made thiophene and phenyl group. He made trans. Here phenyl, thiophene. He asked me to, find out. I told him it's not possible. It's going to be disordered because phenyl and thiophene can occupy the same place. So when you try to hack them, they're always in one unit cell this way, the another unit cell, the thiophene on this side. So what you see is the average structure, over Avogadro number of molecules in the unit cell, in the crystal. So what you see, the average structure, because you see the average structure, they look like disorder. It is disorder because they occupy the same space. So this is a actual crystal structure of thiophene phenyl exchange disorder. So this is what. So you don't have to. You cannot determine whether it's cis or trans. Maybe NMR will have no crystal structure. No way. Okay. That's one. Yeah. So diaxial interactions are important, as I mentioned, for crystal engineering, especially when you want to make something that is predictable. So when you have the heteroatoms or present, heteroatom means different types of atoms. Then there's a possibility anisotropic interactions. Okay, so deviation occurs, and for hydrogen bonding, this is very important because that will create anisotropic interactions. That will be useful for crystal engineering. Okay, from that point of view, hydrogen bond that comes first into the picture. because it's very strong, it's highly directional, okay, it's highly electrostatic. So we will see that how hydrogen bonds can be used to design or can be used for making different types of packing in the solid state. So we go back to Linus Pauling's definition of hydrogen bond. We are all familiar with hydrogen bonds. We have seen, used it, and for a long time. Only difference is he tried to define the hydrogen bonds as strong force. You know, I mean, under certain conditions, an atom of hydrogen is attracted by other strong forces to two atoms instead of only one, so that it may be considered to be acting as a bond between them. But in the modern definition, they want to replace strong forces by attractive interaction, and also they say that we need evidence of bond formation. It's just a cosmetic things that they have done for the definition. But we are all familiar with the hydrogen bond interactions, how it is important in formation of this chemical structures, double helix and triple helix. And the only thing is here, I mean, we can find the hydrogen bond should arise from attractive forces. Of course, we should have electronegative atoms should be present, and something like this. Two different electronegative, can be oxygen, nitrogen kind of thing. So hydrogen should be more electropositive than X. I mean, most of the time it does. An atom to which is covalently bonded. So you will get this kind of hydrogen bonds. Evidence of bond formation. So of course you can find the evidence, different ways, spectroscopy or crystallography or computational. You can find out the energy involved in these things, and you can very easily show the evidence for the formation. So again, this particular slide, you are all familiar. The way we define the hydrogen bonds using this picture is let's assume that this is CH and this is CO. I mean, I should have used very strong one, but I know maybe you can consider this as oxygen and this is nitrogen. It doesn't matter. Now this is carbon, so this is nitrogen. So it's okay. In those days, what happened? They usually, this is given like this, the hydrogen bonds. Okay. Here, XY. First, you need to give the distance between the two atoms that are not connected directly. Okay, so that distance and HY distance. This is the distance you need to give, and the angle between them. Okay. This is the way. In about 50, 60 years ago, it's difficult to locate and refine hydrogen atoms. Nowadays, it is possible. Because of that, what do they do? They give the distance between the two heteroatoms. And when they give the two heteroatoms, they want to make sure that the distance is less than the sum of the van der Waals radii. For example, for nitrogen is 1.5, for oxygen is 1.6, NO distance. As long as it's less than 1.31, then immediately you can see that there's a hydrogen bond present. So we always do for other reasons also. Whenever you see, whenever you analyze a crystal structure, you look at the interactions, even without hydrogen, sulfur. If the sulfur distance is less than some of the van der Waals radii, immediately you see that there's a new interaction, sulfur interaction, right? So that's what you do here. So that was used, but nowadays, since you can refine, locate the hydrogen atom and refine this, you include them into this bond, into the table, and then you start produce it. And you would see that this table containing different types of hydrogen bonds with different strengths. The strongest one, the angle, it's supposed to be a straight line. That means 180 degrees. If it is 180, is perfect. Most of the time you get, around 180, about 175, 175, something, even 170. Of course, the distance, XY distance is always less than the sum of the van der Waals radii. It is very strong. So the strong one Again, the angle. Sometimes you get 180, don't expect, but theoretically you would get, if you have only this kind of hydrogen bonding present, nothing else, then you get 180, maybe in the gas phase when you have hydrogen bonds. But in the crystal structure, you have other interactions that will distort this particular, although it is strong, it will try to distort this angle. So you always get less than 180. In this very strong one, which is closer to 180, because if it is very weak, even 110 degrees you get, it's bent, highly bent, but still it is there. It is there. Okay. So you would, when I mentioned that if the sum of the van der Waals radii or the heteroatom is less than the particular, the sum, then you have the formation. Based on that, there are so many weak interactions. I mean, I just mentioned hydrogen bond. I did put in X and Y here, but you have NHO, OHO, NHN. There's so many CHO, CHN, even OH pi, NH pi. There's so many interactions that are present. I can talk about it hours and hours, but I don't have time, so I'm not going to talk about it. If you're interested, there's so many reviews, so many books, so many chapters that are available dealing with different types of weak interactions. Okay. Am I going overboard?
I think we can stop. It is up to 12:30, right? I think they have.
Okay, they have classes? No, anyway, I'll stop and we can.
Yeah.
Okay, so we'll continue later. So what I mean to say, whenever you talk about hydrogen, there are so many varieties. I'm not going to the details of all these things. If it is, I mean, usually I ask the students to present it. They go into the literature and then they look at, this CH pi interaction. There are books available, reviews, they come and present it. Anyway, those things are quite interesting, and but I'm not going to talk about those things. But you see what I'm saying. So weak interactions include all these things. Many times that will also decide, will be the deciding factor of the package. Okay. So with that, let me stop and